We're working on graphing some polynomials today, so taking that in behavior and adding it to what's actually in the middle. So when you graph a polynomial, the easiest way to do it is to graph your x-intercepts first. So if I'm finding the x-intercepts on this one, remember that's the points that have y values or outputs of 0. So I'm going to set this function equal to 0 and solve for what makes each factor equal to 0. So I've got 2x equals 0, x plus 3 equals 0, and x minus 2 equals 0, which if you divide by 2 gives me x equals 0, subtract 3, x equals negative 3, and add 2 gives you x equals 2. So that means my x-intercepts are the points 0, 0, negative 3, 0, and 2, 0. So you might notice there's no scale on this graph because these can get kind of crazy, so I usually look at my numbers and then make my own. Alright, I plotted my x-intercepts. Done. Now I need some points between those x-intercepts so that I know what shape this graph has. So you need to try at least one x value in the region between your x-intercepts. So like one x value in between those two x-intercepts, like maybe -1 or -2, and one in between those two x-intercepts. 1, you could use fractions, but I'd use whole numbers when possible. So in that interval highlighted in orange there, between those two x-intercepts, I'm going to pick -1. And in my pink region, I'm going to pick +1. So if I plug that back into my original function to get a y value out, just like anytime you want a y value, plug in your x value, see what you get, you're going to end up with 12. If you plug +1 in, make sure you follow order of operations, all that, simplify inside your parentheses first, you're going to end up with -8. Then just plot those on your y-axis. You might need to think about what scale would be appropriate. I'm going to count by 5s here. So plot them, and then I'll connect the middle part of my graph. Now one thing is, those aren't necessarily local maximum or minimum values, so they don't have to be like the peak of your wave. They could be, but odds are probably not. This is just a general sketch of my graph. If we wanted a more accurate one, we'd have to do more points. We're just looking at overall kind of general graph shape here. Calculus, if you take it, will do the exact graph. We have other methods. Okay, so what's left is our behavior, which if you think about your highest degree term would come from multiplying 2x times 1x times x, everything that has x's in it together, which would give you 2x to the third, determining your end behavior of your graph. So it's an odd degree, and it's a positive leading coefficient, which means your ends are going to look like down on the left and up on the right. So draw those in, and we have a reasonable approximation of our graph. So same here, I'm going to start with my x-intercepts by setting my y value equal to 0, and then figuring out what x values make each factor equal to 0. That would just be 2 and -4, so I have x-intercepts at 2, 0 and -4, 0. Then I'm going to need some points in between, so there's actually only one interval between those x-intercepts. So I'm actually going to do 2 points in that same interval because it would give me a better shape of my graph than just 1 point. So I'm going to do 0 and -1 for my x values to plug in, which if you plug those into your original function, gives you 64 and then 108. So this graph has some very large output values. I'm going to count by, let's say, 10s on my axis. Make sure you label if you count by anything besides 1s. If it's not labeled, we're going to assume you're counting by 1s. So plotting those, it's above the x-axis in the middle interval of my graph here. And then thinking about my end behavior, if you were to multiply everything together, I'd have x squared, because that factors to the second, times x times 4. So you'd have 4x to the third, which has its ends go down on the left and up on the right. And one little connection I want to make here to multiplicity. My factor of x minus 2 had a multiplicity of 2, which remember we talked about means it's going to bounce back and just touch the x-axis there, not cross it, since it's even multiplicity. Versus my other one, multiplicity of 1, which means it crosses there. Let's look at this one because it's a little bit simpler perhaps than some of our others, but that can sometimes lead to a lack of information. So if you find your x-intercepts by setting this equal to 0, there's actually only one x-intercept at x equals -2. So there's not really an interval between my x-intercepts that I should plug values into. I could just use my AND behavior, or I could plug values in on the left or the right side of that x-intercept, which would be a little bit more accurate. But let's just use the AND behavior this time, since it's a rough sketch anyways. If you think about it, your leading term would be -2x to the fourth, because there's 4 factors of x plus 2 multiplied by -2, which means it goes down on both ends, so a rough sketch would just look something like that. So all the others that we've been given have been in factored form, which makes it easy to set them equal to 0 and find our x-intercepts. This time it's not in factored form, but they give us a factor. So we're going to use those factoring skills that we've been working on and divide by the factor that we're given and use that to rewrite this in factored form. So if I do a little synthetic division there, writing down my coefficients and then using whatever makes my factor equal to 0 for my synthetic division. Remember how this goes. We'd have to drop down our 1, multiply 1 times 3 gives us 3. Add those together, you get 0. 0 times 3 is 0. Add them, you get -4. -4 times 3 is -12. Add those, you get 0. And then that's 1x squared, since we started with x to the third, 0x minus 4. So our factored form of this looks like the factor we divided by times the result that we got. And then x squared minus 4 is a difference of squares, so it factors further into x minus 2 times x plus 2. Now we can find our x-intercepts of 3, 2, and -2, and plot them on our graph like we did before. One thing that is a little bit of a pain with this one is to test a value in between our x-intercepts of 2 and 3, we are going to have to use something that's not a whole number. So let's go with 2.5, seems like a good choice. And then in the interval between -2 and +2, maybe I'll go with 0, because I like plugging in 0. I won't make you sit through all of the calculations for that, but if you did it, you'd get -1 1/8 and 12, which you could then make an appropriate scale and plot on your graph. Once you get that accomplished, you'd want to think about your end behavior, which apparently odd degree x to the third is popular. It's again going to have my ends going opposite directions, down on the left, up on the right, since it's a positive leading coefficient.